Good morning to today's speaker, resource person, Professor Bhujanga garu, and head of the department, Dr. Rasool, and participants. So I am very happy you all attending FDP since 7 days. This is the 8th day. So today you will be covered the fundamentals of signal processing, particularly mathematical tools, by Professor Bhujanga garu. So now I am honored to introduce Professor Bhujanga garu. Professor Bhujanga garu did his engineering from the prestigious Madras Institute of Technology in the year 1974. I was born in 1972. Sir has completed in 74. I think more than 90% of year will born later than the year what he did his degree. Okay. Then he joined Electronics Corporation of India Limited, ECIL. You know, it is in a ECIL area, Nagar, as technical officer. Later he retired as a senior manager in ECIL, working in the research and development group for nearly 25 years. He had a passion for teaching, and to fulfill that he left the industry and joined Srinidhi Institute of Science and Technology as an associate professor in the year 2000. Later he was elevated as a professor and head of the department, and to remember is a dean or director School of Electronics. So he worked for 20 years there and took retirement in 2019. Then he joined Geetanjali College of Engineering and Technology as adjunct professor, where I had opportunity to work with him for about 1.5 years. Okay, we were colleagues. Okay, I am happy to say that he is my colleague. Okay, and he retired there in March 2021. So this is a brief details about the Professor Bhujanga Rao. He is very good at fundamentals of signal processing. Last time when I conducted FDP in Geetanjali College of Engineering, SAR's lecture was the first lecture there, fundamental, and we both have given one day. Okay. Same topic, whatever I have explained you on Monday, concept of orthogonality and Fourier series. SAR has covered the later part, okay, convolution, correlation, and all Fourier transforms, all these things. So I request you, all of you, be patient and take the inputs from the SAR. SAR don't use any PPT, only chalk and talk. Okay, so it will be more interaction kind of thing. Any layman also can understand. Okay, so with these few words, now I request Professor Bhujanga garu to take over the session.
Thank you very much, sir. Introduction. In fact, after the introduction and after seeing the strength of faculty present here, I am tense. I am tense not because I don't know the subject. I do know the subject, but I left this subject about 5 years back. This subject called Signals and Systems, Digital Signal Processing. I did teach while in Srinidhi, but I did not teach these subjects while in Geetanjali. And to share with you, recently my wife was fighting with me, what do you do with so many books on signals and systems, analog communication, circuit theory, so many books were there. I was fascinated about network analysis, so many books, maybe very close to 120 books. I said, what do I do? Let me dispose them off to whoever is interested. So I requested one of the professors of Geetanjali, Professor Shaik. So he came to my house. He put everything in the, in the car, dicky, And in 5 minutes, it seems faculty took over because all were good books. And after that, I got a call from my friend, your principal, Dr. Narasimhulu, that could I give a talk on that. Frankly, I didn't even keep my notes. The thousands of pages of notes I prepared, I disposed it off. So I only downloaded from my brain whatever I have. That's why probably I have to take to this mode of teaching or mode of talking, that is chalk and talk. I don't like, but I am forced to do that. That is the background. Okay. But we can make it more interactive. I am strong in fundamentals, no doubt. But by virtue of my age, I might have forgotten some equations and all that. Okay? Wherever that is there, please kindly let me know. Okay. Then, yes, mathematical tools for signal processing is the topic given to me. Mathematical tools for signal processing. I think all of us by now, you must be knowing what is a signal. I am not repeating. And you also know what is processing. You know what is processing of a signal. Okay? So what are the mathematics tools? Mathematic tools for signal processing. For example, randomly something I will write. Okay, something like this is there. And you are asked to simplify, tell the value of this. Can you do it directly? Please tell me. Let us make it more interactive because I don't have pages. Can you answer this without the help of mathematics? Yes. So we go for a tool. That tool we call it logarithm. So take logarithm, it becomes just subtraction, multiplication, addition. Not all these complications of exponents and all that. Then what do? It becomes simple, but you are in a different domain called logarithmic domain. In the logarithmic domain, simple way, simplify it. Then whatever result you get is definitely not the answer. You have to go for the inverse of that. What is that? We call it anti-logarithm. So logarithm, anti-logarithm will definitely help you in answering this perfectly, okay, and in an easy way. That is how we make use of the tools. Tools are to help us simplify our problem, analyze a problem easily, and that is the advantage of that. For example, you have network theory, I said, is my favorite subject. For example, you have a complicated network, RLC network. RLC network you have with so many current sources, voltage sources, okay, dependent, independent and all that, and you are asked to simplify. What do? Can you start only with Kirchhoff's laws and Ohm's law, or you have to go for something else? You have to take, yes? Yes, we go for Laplace transform. We go for Laplace transform again, that the complicated expressions can be linearized. In the linear equations, you write it. Okay, we go for Laplace transform there. Okay, like that. Or to solve a number of sources are there, we go for what are called theorems. Theorems are also the methods, techniques to simplify your analysis. You can't analyze just by using Kirchhoff's voltage law, Kirchhoff's current law. But remember, you can solve any network theory problem just by using KVL, KCL. You don't need any theorem. Then why do you go for theorems? You have the superposition theorem, Norton theorem, Thevenin theorem, so many theorems are. Why do we go for that? Just to help us simplify or get to the answer faster. Okay? So these are the tools are designed to simplify analysis process. Okay? Like that, here also in signal processing we have several tools. The question now is, Why so many types of, so many tools? You have a Laplace transform, Fourier transform, Fourier series. In Fourier series, again, you have complex exponential Fourier series, compact or cosine Fourier series, trigonometric Fourier series. In Fourier, Laplace transform, Z transform, DT, what is that called? DFT, DFS, DTFT. Why so many? ZT, Z transform. Why so many? I expect, I am sure the combined knowledge of this class is much more than my knowledge. I am sure about it. So I expect some reaction. Yes, why do you have so many tools? Is not one tool enough?
To simplify.
Yes?
To simplify the things.
No, to simplify, tool is required. Why so many variety of tools are required? Why?
Some are for guidance, some are for this.
Yes.
And
So,
stability also can be defined.
yes. So, you have variety of signals. You have a variety. For example, you have deterministic signal, random signal. You have periodic signal, non-periodic or a periodic signal. You have energy signal, power signal. So many types of signals are there. A single mathematical tool cannot solve all the problem. Okay? So you have different tools because you have different things. Now, that question, I have a list. I am writing a signal. Is it visible, or you want me to write in a bigger font? Bigger? Okay, okay, I will do that. I write the signal. Please suggest the tool required for this. So the first signal, I call it CTCA signal. Continuous time, continuous amplitude, which is nothing but analog. Analog, another name for, stylish name for analog signal is continuous time, continuous amplitude signal. Okay, what is the tool for this? Tell me. What are the tools that help us processing these signals? Yes, yes, continuous time Fourier series, of course, it is continuous time Fourier series, continuous time Fourier transform, and you have Laplace transform. Is it not? Okay, you have the second one, I call it discrete time signal. I don't write dt, dA. If I write dt, dA, what will happen? Suppose I write dt dA. Dt dA means discrete time, discrete amplitude. What is that? Digital signal, purely digital. So, or you can say it may become a trinary, binary or something like that. So, we avoid this. Discrete time signals can be processed or analyzed by using discrete Fourier series, a discrete time Fourier transform. Yes, DFT, you know, DFT, a powerful mathematical tool, and ZT. These are the tools for analyzing or processing discrete time signals. Okay, next one. We have a random noise. Noise is a signal. All of you know that. So, random noise. Noise itself is random. So, I call it random noise. So, what are the tools you have? Can you use Fourier transform for this? This is where I want to talk something about these fundamentals. Can you use Fourier transform for this? No. Yes, you have to go to probability statistics. You can't use Fourier transform for random signals. Fourier transform can be used only for power spectral density, yes. Okay. At that level, okay. But you cannot use Fourier transform for random signals. Okay. So, I write what is very important is probability and statistics. Okay, I will say probability statistics, power spectral density, yes, it has meaning. It tells something about the noise. Okay. Right. Then you have, because I think most of ECE faculty, how many are there in this? ECE. A good number. Okay. You can also, others can also understand. Noise corrupted a signal. Noise corrupted signal. It is signal is there, but it is terribly corrupted by noise. So tell me what mathematical tool will help you extract your signal from the corrupted signal. Signal is corrupted, but I want my signal back. I'll do something to the noise, suppress it. So tell me what is the tool you have for this?
Random process.
It is not random like this, but the random signal has got deterministic signal in it. Your signal is there, which is corrupted by noise. Okay, in the process of transmission or whatever, but at the receiving end, I have to take back my signal.
That's filtering technique.
Filtering, you must know what frequencies are to be filtered out. But do you know what frequencies? They are terribly corrupted.
Mean square.
Yes?
Mean square error.
Mean square error. Mean square error. Mean square error is only a parameter that tells you something about error. How bad the error is, how much is the error, etc. I am still looking for the right term for that. It is a very popular mathematical operation.
That match filter.
Matched filter. But matched filter means you must know the signal. The behavior of the signal you must know. Then you can use that matched filter. And what we use is correlation functions. Correlation is the mathematical tool, yes. Correlation, you use autocorrelation, cross correlation, different techniques are there to extract the signal from noise corrupted signal. Okay, so correlation, you know, that is one of the most powerful mathematical tool. Okay, next, I want to take the output signal of a system, LTI system. Output signal of an LTI system. LTI system, I will talk something about it. Okay, I prefer to talk the very basic things. If you have any doubts, please express. I will be happy to clarify that. Okay, even any kind of problem in this. Okay, tell me. Output signal, it is a signal to be processed. It has come out of an LTI system, linear time invariant system. Okay, what mathematical tool will help you? Yes.
Sir, Fourier transform we can apply.
Fourier transform will help you translate, going from time domain to frequency domain. Okay, you want to see what is in the other side, the frequency domain side, use this tool called Fourier transform. Okay, but I don't want frequency domain, only in time domain. Output of an LTI system. How do you find the output of an LTI system? I think you all know, maybe I am not able to ask the question properly. The output of a system, LTI system.
Transformation.
Convolution.
Excellent. Convolution of what?
X of t convolution.
Input signal must be convolved with the impulse response of the system, and it is applicable only to LTI system. Convolution you cannot use for non-linear systems. You can use only for linear systems. Okay, right? So convolution I have not written. Actual powerful tool is convolution. Yes, it is a very powerful tool. Convolution is another mathematical tool. So that's why so many types of mathematical tools are there. And what about if a signal is non-stationary? If a signal is non-stationary, I want to know something about it. What tool should I use? Non-stationary signals. You know non-stationary signals, have frequencies which change with time. That is a very important thing. Frequency is a function of time. Spectrum is a function of time because it is non-stationary. And we go for wavelets and all that. We analyze such things. We window the signal and consider that to be stationary in that narrow window, and then use our tools, well-known tools, Fourier transforms, then keep on moving the window to cover the entire. That's what we do. Okay? So, non-stationary, we go for estimation methods. We estimate the power spectrum and others. So, estimation, this is a mathematical thing. So, I am talking both electronics and communication as well as mathematics. These are all the mathematical tools which find direct application in our subject called signal processing. Okay? Any doubts in this until now? Or can we add to the list? I'll be happy. But of course, this can be divided into periodic, non-periodic, all that you know, Fourier series or Fourier transform. So my question, one question I will ask. Please, in order to make you active, I keep asking questions. Can I apply Fourier series to non-periodic signal?
Only periodic signals we can apply.
So you are saying no. Only period. You are also saying no. Is there anyone who says yes, it is possible? My question I will repeat. Fourier series is defined for periodic signal. We know different types of Fourier series are there. Fine. We know the meaning also. Sir has developed that series, how it has come from the property of orthogonality and all that. That is okay. But tell me, can I use that Fourier series for a non-periodic signal? For example, I have only a signal like this. This is the age problem. My writing is supposed to be very good. Now it has become bad. Okay. Some values you can give always. And this is a signal f of t. Let us say it is a voltage pulse, current pulse. Can I think about Fourier series for this?
So if we bound the Fourier series, then we can get the Fourier transform of that.
No, don't talk about Fourier transform. I am only talking, can you find Fourier series for this? Is it applicable or not? I think you know the answer, but you are not coming. Please talk something. Okay, doesn't matter, it gets corrected. I am there to correct. Yes. Yes is the answer. You said it partly right. The Fourier series, whatever you obtain for a periodic signal, limit it to that period. -1 to +1, -1 less than t less than 1 is the interval of validity of that Fourier series. Strictly speaking, Fourier series was defined only when you extend this signal. Oh, sorry. Any other better method is there? Okay, I will keep this in mind. Okay, right. I think I can reach. Okay. It's okay, no problem. I don't have a problem. Now and then you have to correct me. Okay, right. So Fourier series, yes. The orthogonal set of orthogonal sets, signals, whatever you have, sine and cosine wave with a constant, trigonometric series, whatever do you say, elementary signals, or you have exponential complex, whatever you can express. But say that that series, whatever you are writing, is valid only for -1 less than t less than 1. I am saying less than -1 less than t. I am not saying -1 less than or equal to t. Why? Because there is a jump discontinuity at t is equal to -1. At discontinuities, the Fourier series does not converge. You write f of t is equal to a naught by 2 plus e, what is that called? a1 cos omega t plus a2 cos 2 omega t plus and so on, and sine terms, all infinite terms you write, right? Okay? These terms must be limited to only this interval. I am not going to frequency domain, I am only talking about time domain. So answer is yes. Okay? Right. Now, okay. Now going back, Fourier transform. Fourier transform, we say Fourier transform. Can I apply Fourier transform to periodic signals? Similar question. Can I apply Fourier series to non-periodic signal? Was the question we answered. Yes, provided you limit the series to that interval of validity. Similarly, my question now is, can you apply Fourier transform to periodic signals? You must have used it. Is it not covered? Then I can start from fundamentals, no problem. Because I like that subject. But I am under the impression, because you have already completed more than 9 days of this program. Most of these things are covered. So maybe I thought it will be too fundamental, whatever I am talking. But if you don't think so, I can still go into fundamentals, not a problem. Okay. Can you use Fourier transform for periodic signals? My question, please write that question and put your mind, take a few seconds, think about it, then you will understand that. Yes? Yes or no?
Yes.
Yes? Yes? Only 2 yeses out of... Yes?
Yes, sir.
The answer is yes. Then what is the condition? Previously I said, you have to limit the Fourier series to the interval. Then you can say yes. Now I am saying, again we are saying yes, Fourier transform can be applied to periodic signals. Under what condition? Any conditions or unconditionally? Yes? Dirichlet's conditions, absolute integrability. Okay, satisfied. Absolute integrability. Yeah, number of discontinuities should be finite. Amount of discontinuity should also be finite. Okay, these are the conditions. Yeah. That is okay. That you are saying, I am stating the conditions, Dirichlet's condition for the existence of Fourier transform. Satisfied. Now my question is periodic signal. Periodic signal, Fourier transform. Do they go together? We said yes. Then what is the condition?
Sir, like in sampling, we will multiply a signal with periodic trail of impulses. So here also you can go with the impulse function.
Yes, I am just bringing that concept. Impulse, if you allow impulse function to exist, the answer is yes.
Yes.
If you don't allow impulse function to exist, no. So what is this impulse function? You know what is delta of t? Unit impulse in the continuous time domain. And delta of n? We call it unit sample. Rather than impulse, we call it unit sample. This is in the discrete domain. It is well defined. There is no doubt about it. it is equal to 1 for all n. No. For n is equal to 0. And 0 for all n, all other values. For all. So there is no dispute about this. It is well defined. Okay. And we are happy because discrete time signals are computer friendly. And computer doesn't understand infinities. And that problem we have in the continuous time domain, because this is not defined, it is defined only at t is equal to 0, and that value of this one we don't write, it is infinity at t is equal to 0 and 0 for all values of t other than 0. So recording stopped. Oh, it continues. Good. Light is not a problem. Right. Light is required for them to see the board. So, what kind of signal are we talking about? It is, in the real sense, delta of t is not a signal. It is not well defined. Then why do we talk about something which is meaningless? It is meaningless. It is defined only at one value of t, that is 0, and that too its value is infinity. But there is something great about it. That is called the strength of the impulse. The strength of the impulse is defined as the integral of that function right from minus infinity to plus infinity. This is equal to 1. Okay, this is well defined. What is well defined is the strength of the impulse. I think you must have seen how it is obtained. You know that? So I'll just show you that. For example, t is equal to a, the pulse width is a, and pulse height we call it 1 by a. 1 by a. So the area obviously is equal to 1 by a into a. It's the area of a rectangle, so it is 1. Now I make a tend to 0. Okay, if a is replaced by a by 100, it will be 1% of this value. But this will become a large value. Okay, this will become 100 by a, and this becomes a by 100. Still the area remains the same. What happens if a tends to 0? It should be valid. A is infinitesimally small, we have seen. But I want to make it really 0. Then the height will become really infinity. Height becomes infinite, width becomes 0. Still we are talking about the area of a figure, rectangle, which is well defined 1. That is called the strength of the impulse. Okay, strength of the impulse is that. Okay. So anyway, what is use of this? You can express signals in terms of impulse functions and shifted impulse functions, weighted and shifted impulse functions. Weighted means multiply this delta of t with some k. K delta of t is nothing but an impulse function with strength k units. Okay. So I'll give a nice example, circuit example, to see how that impulse has some meaning practically. I'll give that example. Okay. So my interest is, does Fourier transform exist for this? Because Fourier transform is what? Fourier transform by definition is integral minus infinity to plus infinity. Whatever is the function, you are saying it is a delta function, e power minus j omega t dt. This is just by definition of Fourier transform of a function, that a function is the delta of t. Okay? And we know delta of t, when you integrate from minus infinity to plus infinity, whatever is multiplying it is the strength of it. In fact, you don't have to integrate it. Just take a look at what is multiplying it. What is multiplying it? E power minus j omega t. And at what value should I evaluate that? T is equal to 0 only has a meaning. All other values it is 0. So if you put t is equal to 0 in this one, you get e power 0. So the 1. Okay. What do you understand by saying the Fourier transform of a delta of t is 1? Tell me, what do you understand by that? I am saying like this. Fourier transform of some function called impulse function is 1 for all frequencies. What is the meaning of that? I don't think there is any other function where every thinkable frequency is present in it. Because it is 1 for any frequency. It is independent of frequency. That means if you plot the spectrum of this, it will be like this. Yes, all frequencies are present up to minus infinity to plus infinity. Is it possible to reconstruct delta of t? Yes, it should be possible provided you give me all thinkable frequencies right from 0 to infinity. Okay, so that is the spectrum of an impulse function. So why then we talk about impulse response? The reason is we want to see how the system behaves for different frequencies. But at the input, what I am giving all frequencies equally strong. 1 means all frequencies are strong, equally strong. Okay, all have the strength 1. So that means I am giving the same same frequencies, all frequencies at the same strength. What do I get at the output depends on the behavior of the system, the transfer function of the system. Some frequencies are stopped, some are attenuated to less level. All that happens because of the behavior of the system. But at the input, I am providing all frequencies equally strong. That is the meaning of impulse response. So impulse response has got very great significance in communication systems, particularly electronics and communication system. Okay. And what about step function? What is step response? You must have heard about step response. What is step response?
Applied unit step.
Yes. So the output of a system when the input is a unit step. Okay, that is step response. That is also very important. Step. I have not shown this. Okay, this is a step function u of t. So it is unit step. So it is 0 for all negative values of t. It is 1 for all positive values of t. This is a unit step occurring at t is equal to 0. It can be delayed, advanced, all that is possible. So step response, people talk, particularly communication engineers. I worked in industry. We always used to test the equipment, whether it is a transmitter or whether it is a receiving unit. What is the step response of it? It is so important. Why it is important? Because impulse cannot be generated in the laboratory. Whether it is your laboratory, college laboratory or industry laboratory, R&D lab, you cannot generate impulse function. Okay, that is only theoretical fiction. But you can generate a step function. After all, what is a step function? A DC voltage switched on at t is equal to 0. Close the switch, you will get 5 volts. Open the switch, 0 volts. So that is step. Step is very easy to produce. So that's why we used to have the step response. So why? The question is why? Why is it important? Can somebody tell me why step response of a communication system or any processor is important?
You have to find out the error, sir.
You have to
Input to output, you have to find out the error. That's why we have to use step functions.
step function, you are giving step at the input. Current or voltage, whatever you are giving at the input to the system. Output you are seeing, monitoring using an oscilloscope or spectrometer, whatever. You are seeing that. So why is that step response important? That is my question. Impulse, I said, you cannot generate impulse, otherwise it is the best. Ideal test signal for any equipment is impulse. But you cannot produce it. So we go for step. So step response is important because if you can recall, I don't know how many of you remember the Fourier transform of a step function is equal to, tell me, Fourier transform of a step function, unit step function.
Pi del of omega plus 2 by j, 1 by j.
Pi
Del of omega.
del, is it 2 pi or pi? Pi delta of omega plus
1 by j omega.
1 by j omega. So what is this? Again,
Half of the step function and half of the signal.
the greatness of this is that step function has got the least frequency in it. What is the least frequency? Constant. Constant is what? Zero frequency. And it has the highest frequency delta of omega. Because it's high, okay, so it contains both highest frequency and lowest frequency, so it tests for both at one step. In one step, it tests for the entire frequency range, high and low. That is the greatness of this step response. Okay, I said I will give you an example for impulse, practical example, circuit example. After this, I will use it. Any doubt until this?
Sir, what is the result for Day-9 non-periodic periodic Fourier transform of the periodic one?
Okay, I stopped there. That's right. So, Fourier transform of a periodic signal. So, I will say periodic signal f. I will put t for the time period of the function. So, there is a signal f of t which is period in time t with a period capital T. Is it clear? What is the Fourier transform of this? Strictly speaking, it does not exist. But loosely speaking, it exists. Let us talk loosely for some time. Okay? Because we forced Fourier transform onto periodic signals. How did you force it? Let us see. So, I will say Fourier transform of this, because it is a periodic signal, can I put it in complex exponential Fourier series? You know, a Fourier series, how many types are there? Trigonometric Fourier series, compact Fourier series or cosine Fourier series we call it, and then complex exponential Fourier series. So, let me put that one in complex exponential Fourier series. So, I will write this one as Fn e power j n omega naught t, n running from minus infinity to plus infinity, n is an integer. Is it not? That's all. You said it is periodic signal. I am expressing that in complex exponential Fourier series. What is Fn? All of you know. What is Fn?
1 by t.
Yes, Fn are called complex exponential Fourier coefficients. Complex exponential Fourier. This is 1 by t integral over a period, any time to any time, one period of interval you have to cover, and whatever signal that is given, that is ft of t. I think this suffix t I used to differentiate it from non-periodic signal. It's a periodic signal with period capital T. If you don't like it, remove it, doesn't matter. Okay. And e power minus j n omega naught t dt. These are Fourier coefficients, complex exponential Fourier coefficients. What do they tell? Orthogonality length. Tell me, what is that Fn? Fn tells what? Fn, nth harmonic coefficient. N is equal to 10, you put, what is F10 I am asking? F10 is the strength of the 10th harmonic. The strength of the 10th harmonic. In what? In f of t. That is present. So many frequencies are present, 10th harmonic, how strong is it? That is given by Fn, okay, or F10. So this is only the strength of that is indicated. This is called the analysis. This is called analysis equation. And this is called synthesis equation. You all know what is synthesis equation? Combining parts to make the whole thing. That is synthesis. What is analysis? Breaking the whole thing into parts to know what it contains. What is the makeup of it? How is it made of? Okay, that is indicated by this analysis equation. F0, F1, F3, F4, etc. are indicated by this. Okay, anyway, my question is not answered yet. This question, tell me. Okay. Is it okay? Okay, right. Right. So I want to know what is the Fourier transform of this function? Come on, can somebody help me? Yes. How to proceed further? I put something, I have not answered your question. You only asked, right? Yeah. I am very good at digressing the topic, going from this to that. So thank you very much for bringing me back to it. Okay, you asked me about that practical example, circuit example for delta of t. Okay, please remind me. Right. So this summation is with respect to an integer n, running integer n, harmonic number. N is a harmonic number. And when you are saying Fourier transform, you have to perform integration. Okay. So integration is with respect to what? With respect to time. And summation is with respect to n. These two are independent of each other. So I can interchange the operations. So if I can interchange the operation, why not I bring this summation outside? And Fn has nothing to do with integration. It is a constant. It is a number. It only gives the strength of the nth harmonic. So I take out that also. Then I will push that integral minus infinity to plus infinity, and you have e power j n omega naught t dt. This is the Fourier transform of that. One small step I have skipped. I don't think there will be. Fn is a constant. I took it out of the integration. Okay, and then the definition of Fourier transform I have put. That's all. So now, what is this e power j n omega naught t? Here we call for a property called frequency shifting. After all, e power j n omega naught t does what? It shifts in the frequency domain. It is a phase shifting term. It is not its magnitude is 1. You all know that magnitude of this is 1. So it only provides the phase angle. The angle is how much? N omega naught t. That is the angle. So angle depends on n value. It changes. Okay. What does it mean? I am multiplying something with a complex exponential. It is frequency shifting and nothing but frequency shifting of what? Still I don't know. So I will put Fn, n running from minus infinity to plus infinity. And here I will say integral minus infinity to plus infinity 1 into e power j n omega naught t dt. I want to see, because e power j n omega naught t only shifts the frequency, nothing else. So what is required? Fourier transform of 1. You have to find Fourier transform of 1. I think all of you know the answer. If you don't know the answer, I will do that. You want me to solve, or you know that answer? Answer, if you know, you just write down. So I will write sigma n running from minus infinity to plus infinity. What is the Fourier transform of 1? Yes, Fourier transform of 1 is nothing but Fourier transform of limit a tend to 0 e power minus a mod t. This is limit. E power minus a mod t, as a tends to 0, it is nothing but 1. In place of 1, I have put this. And we know how to find the Fourier transform of e power minus a mod t. What is mod t? Plus t if t is positive, minus t if t is negative. Mod t is plus t if t is positive, minus t if t is negative. Okay? So, a few more steps. You have to know what is the limits and all that. It's very simple. Okay? So, the answer is Fn is a constant, put it, and it is 2 pi. 2 pi delta kada. 2 pi delta of omega is for this. 2 pi delta of omega is for 1. But 1 is getting multiplied by a complex exponential, means it has to be shifted in the frequency. By how much? N into omega. So omega minus n omega naught. ఇంకా ప్లస్ లేదు ఏం లేదు, అయిపోయింది. దట్స్ ఓవర్. దట్ ఈస్ ఆన్సర్. If you want, you can remove that 2 pi outside. Nothing else can be done. Because Fn cannot be taken because sigma is with respect to n. Okay? So this is, now tell me what is happening here. We said first, we suspected that Fourier transform does not exist for periodic. We want to see. Okay, if you want to see, you have to face the music. What is the music? Impulse functions. Impulse function train is coming. The train of impulses, whose strength is 2 pi times Fn. Okay, the first impulse, if you take omega n is equal to 1, if you take n is equal to 1, just think of 2 pi f1 and omega minus omega naught. Okay, that is what? That is your Fourier. So Fourier transform exists if and only if, that you have to say, if and only if you allow the Fourier transform of 1. If you say yes, I will allow Fourier transform of 1, which does not exist otherwise, then all this is possible. How did he achieve that? I manipulated 1, because 1 I cannot integrate, it becomes infinity. So what did I do? In place of 1, I have put something like this: limit a tending to 0, e power minus a mod t. I have made use of this. See how many mathematical tools we are using. Limits. Okay, then approximation. So now I will, any other questions on this? Right? So what is the answer? Fourier transform exists for periodic signal if and only if you allow Fourier transform of 1, which otherwise doesn't exist. That is the answer for that. Okay? Now we'll go back to that. This is my favorite way of explaining impulse function. I will explain this. Most of you must have gone through it. See this example, my favorite example, to explain what is delta of t. Delta of t, is it a mathematical fiction or does it have any physical significance? This will tell you. Okay, I will now ask you a question. All of you know C dV by dt is the current. Okay, if voltage is V, C is the capacitance in farads, then C dV by dt will give you the current, and my question is what is I of t? As simple as that. Tell me what is I of t. What is the current that flows through the capacitor? I have given C value, okay, and I have given voltage function. Instead of a mathematical equation, I have given a pictorial representation, a graphical representation of it. Okay, both are same. Now tell me, come on. So the first step is, of course, you must know that the current through a capacitor is C dV by dt. This you must know. Okay, knowing this, now what is dV by dt? So first let me, come on, tell me what is dV by dt. So I will plot dV by dt with respect to time. It is differentiation of this. So that means there is a slope. Slope is opposite side by adjacent side. K by T naught. Okay. So K by T naught is the value until T is equal to T naught. Because slope is same. There is some problem here. Okay. T naught. So the value of the differential dV by dt is K by T naught until T naught. And after that it is a constant, therefore it will be 0. It is 0. 0 is the value of this. Okay. So what is C dV by dt? Simply multiply with C. So the current I of t is nothing but C K by T naught. Okay. Up to T naught it is 0 otherwise. After that it is 0. And together. So we answered. Now I want to see the limiting case. If T naught tends to 0, what will happen? T naught tends to 0 means make the T naught as small as possible. Infinitesimally small, ultimately 0. So what will happen? The area remains the same. What is the area of this? I of t. I of t is what? C dV by dt. So C dV by dt is this. Now I want to integrate I of t with respect to time. So minus infinity to plus infinity. So what I will get? If you integrate current, it will be charge. Current into time, ampere second is charge. So I am asking what is the charge? Charge can neither be destroyed nor. Therefore, that remains the same. That is a finite quantity. That is like your strength of the impulse. The strength of the impulse is the charge. So tell me, what will happen to the integration? It is nothing but area. Integration is nothing but area. Area is nothing but T naught gets cancelled. So CK is the area. So CK coulombs because it is charge, current into time. Okay, CK coulombs is the charge on the capacitor. Fine. Now I am asking you a question. What will happen if T naught tends to 0? It doesn't care. The charge does not care. It remains CK. CK coulombs remains CK coulombs. But what will happen to the current? What will happen to the current if T naught tends to 0? You have got an impulse current. Current becomes impulse. So we call it impulse, current impulse. But remember, current impulse means it is not amperes. It is what? Current impulse? Charge. Because you are multiplying width and height, right? So time into ampere current into time. Therefore it is charge. Okay. So this is a good example to show that if you allow that infinite current to flow through the capacitor will definitely get spoiled. Infinite current it can't take. Okay. But remember, infinite current for how long? 0 time. Then what is the result? It has charged the capacitor to C into K coulombs. Okay. Though the time is 0. So this is a good example. Similar example you can develop yourself. Current source, inductor. You all know L di by dt will give you the voltage. L di by dt will give the voltage. Similar thing can be done. Okay. Right. Okay. Oh. Now a very interesting topic or the doubt what I got first when I learnt Fourier transform, jet transform, Laplace transform, I got a doubt. Why is it done like that? For example, I will talk about Laplace transform of a signal f of t. We use this letter symbol f of s, capital F of s. So what is the, come on, tell me, what is the definition for this?
Integral minus infinity.
Integral minus infinity to plus infinity,
X of t.
f of t
E power minus st.
e power minus st
dt.
dt. That is called unilateral. Absolutely no problem. This is better than that. Because if the signal f of t is one-sided, right-sided, you can start from 0. If it is not right-sided, it starts from minus 1 second. Still you can use this, not that. So it is always better. This is more powerful than that. Absolutely no problem of using this. This is called bilateral. That is called unilateral. Okay? Unilateral. I will write that. Yeah, one-sided. One-sided is unilateral. Yeah. So this is what is called bilateral, right? Bilateral L of t, and of course if you put this 0 to infinity f of t e power minus st dt, this is unilateral or one-sided. And here also you see in books, some books you see this 0 minus, some books you see 0 plus, some books you see 0 only. Is there any difference between these three? 0 minus, 0 plus and 0.
Initial conditions, sir.
Yes, if there are initial conditions, you must go for 0 minus. If there are no initial conditions, you have to go for 0 plus. If there is an impulse at t is equal to 0, you must use 0 only, because 0 is included. Don't think impulse disappears after 0 time. It does the damage. You have seen that. That impulse flown through the capacitor only for 0 time, but it has put charge CV in it. So that's all. That is the difference. If impulses are there at t is equal to 0, use 0 minus or 0. Initial conditions you must use 0 minus. Okay, no initial condition, 0 plus. Okay, right. Now my question is, my doubt I want to share with you, and you also must have had that doubt, unless you have accepted what is done to find the Laplace transform. Similar thing is there for Fourier transform. Similar thing is there for jet transform. What are we doing? The given function is multiplied by a transforming function. Here the transforming function is e power minus st. S is a complex frequency variable. Why complex frequency variable? Because it is more general. If S is equal to j omega, it is a Fourier transform. Fourier transform, Laplace is more powerful than Fourier transform. LT is more powerful. Anyway, so what are we doing? Give me a function. Yes, f of t is given to me. I am multiplying with an exponential function. Here in this case, e power minus st. Then I am finding the product, summation. Summation integration is nothing but summation from all the way from minus infinity to plus infinity. What is that I am doing? That is what I want. That is what I used to get a doubt. I got the answer, which I want to share with you. I think some of you must be knowing it. Why should we multiply with e power minus st?
When we multiply an exponential factor, it will be shifted in frequency domain.
That is a property, but that is provided it is a complex frequency term. But here, real and both will be there. Sigma plus j omega, e power minus sigma t is there, multiplied by e power j omega t, minus j omega t is there. So here that is not applicable. It is not frequency shifting. It is a transforming function. Yes. No, that is okay. So that's what, you have accepted the formula. I have not accepted the formula. For example, when I say Fourier transform, I am saying f of omega is equal to minus infinity to plus infinity f of t e power minus j omega t dt. Okay. Here also we are multiplying with an exponential. So multiplication is the most powerful, remember, most powerful mathematical tool in our electronics and communications. The most powerful.
And we are having some different transforms also. Angles transform something.
Which?
Integral transform.
Yes.
If we replace the kernel by this e power ist or like
Yeah.
different.
Yes.
Sometimes we are replacing by e power s minus in some different function also.
E power?
Kernel.
Okay. But why do we multiply with that? That's my question is, why do we multiply the function with some other thing? That's my question.
Actually, just convolving two signals.
We are not convolving, we are multiplying and integrating.
Sir, actually in a spectrum, if we get more number of frequency or harmonics, if we want to draw, in order to plot that frequencies in a spectrum, we are using the exponential.
Okay, we'll go to this later. We'll talk about this because sir is saying it's, frequency spectrum. It's like this. F of t is a function which has got so many frequencies in it. When I compare two signals, what do? I multiply them. Comparison of two signals involves multiplication and finding integration, right? So I am multiplying the function with e power minus j omega t, means I am comparing these two signals. Okay, f of t is compared with e power minus j omega t, which is a revolving phasor. It rotates because e power minus j omega t rotates in the clockwise direction. Clockwise is negative, you know that. So it is a phasor which is moving with omega radians per second. Doing what? Searching for the frequencies present in f of t. That is what it does. It keeps on moving because t is a running time variable. Nobody can stop. Time and tide wait for none. It keeps on moving. Doing what? Searching at different times. Okay? To find what are the frequencies present in it. That is how you get a function of frequency here. Okay? So, a function of frequency here. So, it is a matter of comparing your given function with sine or cosine. Both are present in e power minus j omega t is what? Cos omega t minus j sin omega t. You are looking for the sinusoidal components in it. Okay, exponential comprises both. Okay, so comparing is what we are doing. And comparison is very good. They are very nice, very good friends. Then you get a large value upon integration. If they are enemies, you get a large negative value. If they are strangers, 0. Stranger is what? Orthogonality. If two signals, if these two f of t and that x, whatever you are multiplying with, if they are orthogonal, the answer will be 0. So strangers are orthogonal, good friends or best friends are the perfect correlation, large positive value you will get upon integrating this. Large negative value, enemies, we say enemies, but then it is opposite. Enemies know each other very well. You know, enemies know. If he goes this way, this fellow goes this way. That's why large negative value you will get. Okay? So negatively correlated. Strongly but negatively correlated. Strongly, positively correlated. Not at all correlated. Strangers, orthogonality is that. Okay? Right. So, the purpose of multiplying the given signal with any signal is just to compare whether that is there in it or this is there in it. Because A into B is B into A. And our searching function is this in Fourier transform. Our searching function is this in Laplace transform. What is S? S must be having units of 1 by t. T is time. So S must be 1 by t. 1 by t is frequency. So that's why we call it frequency variable. So in general it is complex, therefore sigma plus j omega is what we take for this. Correct? So this bothered me a lot. When I found the answer after learning what is that comparison, correlation, we have seen how to compare two signals and all that, mean square value, all that is behind this. Now, please tell me how much more time is there? 40? 30 minutes. 30 minutes. And I have not started discrete time. Okay. Fourier series, we'll talk a little bit about Fourier series, more about it. What is the meaning of it? So f of t, which one we'll take? We'll take this one only. This is a trigonometric Fourier series. Fine? So tell me something about it. It may be a voltage, or it may be a voltage input to an LTA system. It can be anything. Current. Okay. So what is the meaning of this? A0 by 2. Why did we put that A0 by 2? I always say this is DC plus this. The DC value. It is average value. DC value. For some integration, for some standardization of that integration, we have put A0 by 2. Not at all required. And if you pass this f of t, if it is a voltage through a capacitor, here you will get f of t minus A0 by 2, right? Because capacitor will block this DC outside, you won't get DC. So it is just a DC value. You can write A0 or A0 by 2 or A0 by 10 or K or something, whatever, it doesn't matter at all. Okay? So if there is an average value, the first term will not be 0. And what is this AN? Coefficient of cosine function. So what is that AN? Does it tell something? AN. Okay. Okay, I'll say n is equal to 1. Our friend is answering this. What is A1? Is it complete strength of the harmonic, first harmonic? Only part of it. Yeah, because sine is also there. So, A1 square plus B1 square under root, that will be the strength of the first harmonic. Isn't it? Because both are having the same frequency, fundamental component. So, this will tell you whether first harmonic is present or not in the frequency. The strength of it. So, this is, for example, when you take the two signals, for example, these two signals you take, like it is A1 cos omega naught t and B1 sin omega naught t. You take these two signals, the two terms, out of infinite terms, you take only these two terms. Tell me how they are related. A1 cos omega naught t and B1 sin omega naught t. Can you say something about their relation? Are they strangers, best friends, worst enemies? I will repeat the question once again. I have put two terms out of infinite terms, asking for their relation or correlation or whatever you call it. Are they related or are they strangers? They know each other or they don't know each other? Don't know each other means orthogonality, remember. They have nothing in common. Nothing of this is in that, nothing of that in this. They don't know each other. Do you agree with that? That is what you are saying, orthogonality. Orthogonality is nothing but that. Orthogonality, all these terms, infinite terms, they do not know each other. That means they don't contain anything of the other. A1, A2, A3, they only talk about the strength of that particular first fundamental, second harmonic, third harmonic, etc. I mean, along with B1, B2, B3. Okay? So, that is how it is formed. So, you take out the error. Okay? Error should be minimized. That is what mean square error. We have set it and then we have come to this. I think sir must have explained yesterday what is orthogonality. That is how we got this. Okay? Right. Yeah.
Sir, mathematically, if you see, f of t we are expanding as a Fourier series. That is basically a periodic function.
Right.
Mathematically, if you see, the sine and cos is also periodic. But mathematically, a naught by 2 is something
A naught by t.
balancing something.
I will explain that. I will explain. Suppose you have a function like this. This is a periodic function. Let us say it is a voltage function. Okay? So we can find Fourier series for this. Can we? How can you find Fourier series for this? By finding three things, that's all. What are they? A naught by 2. The average value is 1 by 2. By inspection you can find the average value of this. This function is 1 by 2. And an you can find the cosine components, and bn also you can find out by using your analysis equations. What is an formula?
2 by t integral 2 by t
An is 2 by t integral over a period, any one period, f of t cos n omega naught t dt. So what are you doing here? You are finding out the strength of the cosine component of the nth harmonic. And together an. Similarly, bn will give the sine component. Right. Now, what are you doing here? Can you just see inside?
Multiplying.
Yes, again you are multiplying your f of t with a particular component, the nth harmonic component, and seeing whether there is anything. Yes, there is something, then an will not be 0. There is nothing of that harmonic is absent, you will get an 0. Okay? But I did not answer your question, now I will answer. Suppose I shift the same function down. I will draw another function g of t. G of t is nothing but v of t minus 1 by 2. Tell me what happens. What am I doing? The same function. I am just subtracting 1 by 2 from that. I am just shifting the waveform about the x-axis. Shifting the waveform about the x-axis is nothing but adding a DC component. I remove it. Do you think what will happen? Nothing. Except that first term. No, not that. Not that. Shifting about the x-axis. Yeah. This shifting is time shifting. I am not talking about short time shifting. I am shifting it, amplitude shifting, up and down. Okay? So when I shift it, it will be like this. It will be like this. So you will get half here minus half here. Other things remain the same. Time period doesn't change. So all the things will be there. So if you know the Fourier series of that, all that you need to do is subtract that DC component. Suppose I will form another signal that I will call it x of t. I will say x of t is nothing but some constant a times v of t minus, let us say t minus t naught. So how does it look like? I think I must give some value so that it will be clear. T minus, let us say 10. T minus. So what am I doing here? I am multiplying with a constant. Multiplication with a constant is nothing but amplification. If that constant A is less than 1, attenuation. More than 1, amplification. So that's called homogeneity or scaling, magnitude scaling. And time shifting, I am delaying by 10 seconds. Can I use this formula, this first Fourier series, whatever I found, can I use it for this? Why not? What do? Wherever t is there, put t minus 10. And the whole series must be multiplied by that number A. A is an amplification process. Okay, that's all. Suppose I pass this, V of t through a differentiator. What do you think will happen? I pass it through a differentiator. dv by dt. Every term you have to differentiate and accept some impulses, because if there is a jump, there are discontinuities, there will be impulses. Okay, so that is the power of it. Where is this coming from? Where is this coming from? It is coming from the property called principle of superposition. Principle of superposition. What is that principle of superposition? We call it, in signals and systems or this, we call it linearity. Linearity is another name for the principle of superposition. Principle of superposition is nothing but additivity. Linearity is equal to, yes, homogeneity plus additivity. Homogeneity is what? Amplitude scaling, multiplying with a number constant. That is homogeneity. Okay. If input is x of t, output is y of t, then if I change the input to 2 times x of t, I must get 2 times y of t. That is homogeneity. What is additivity? If I give x1 of t, I get y1 of t. I get x2 of t, y2 of t. Why not I give both together, x1 plus x2? I must get y1 plus y2. That is called additivity. Additivity and homogeneity together, we call it linearity. Linearity is nothing but the principle of superposition. And this is what we are using in this, because Fourier series is a linear operation. Fourier transform is a linear operation. They are linear. Jet transform is a linear operation. They are all linear operations. Okay? They appear to be non-linear. For example, when I say the voltage across an inductor is given by L di by dt. A inductor system, is it linear or non-linear? That is where you have to apply homogeneity and additivity. Homogeneity, additivity, I will apply. Both I will apply here. So, voltage across an inductor is L di by dt. Right? Now, what I will do? I will apply I1 as the current. I1 is the current. Then I will get L di1 by dt. The voltage across inductor is L di1 by dt. I apply, let us say, A1 times a constant, A1 times V1t. I will get A1 times L di1 by dt. Next time I will say B2 times V2t. First V2 is L di2 by dt. Okay, and I am multiplying with B2, YB2, A2 I could have used. Anyway, now suppose I apply both V2T. Definitely I can add these two. That means I am homogeneity, multiplication as well as additivity. Therefore, it is a linear system. Generally, we think only resistor is a linear system. No. Capacitor, inductor, they consider as linear. And of course, time invariant also. Time invariant capacitor C farads remains C farad tomorrow also. Yesterday also.
Energy stored in that will be a non-linear function.
Energy stored in what?
A inductor or capacitor.
Yes, okay. Superposition principle is not applicable to powers. That's what you are saying. Superposition principle is not applicable to powers because a plus b whole square is not equal to a square plus b square. Something else is coming. Therefore, it is, yes, you are right. So, that is when it comes to powers in that. Okay? It is not applicable for that. But when you are talking about linear voltage or current, yes. RLC circuit also, it is a linear system.
Yes.
RLC series or parallel circuit, will it not give rise to linear constant coefficient differential equation? When you form an equation, linear constant coefficient differential equation is obtained. It is a mathematical model of an RLC circuit. Okay. Is it not a linear differential equation? How can you say it is a linear differential equation if the circuit is not linear? Yes, RLC circuit is a linear circuit. It is an LTI system. That's why we are able to apply the two homogeneity and additivity. Okay, you have to understand that. Okay, right. Any other doubts? First priority will be given to clarifying your doubts.
Sir, in Laplace transform, why
Yeah.
multiplying with exponential that one?
Okay. The exact answer for that, S-plane is more general than an imaginary axis. Okay, this is the imaginary axis. So S is equal to sigma plus j omega. So I put sigma is this, j omega axis is this, imaginary axis is that. Okay? Now, when you are talking about Fourier transform, you are only operating on the y-axis. You are not bothered about anything else. Okay, you are doing everything on the imaginary axis. But Laplace was much more senior than Fourier. I don't know whether you have seen the literature and all. I think he was examiner to Fourier at some point of time. Fourier came later. And he said, let me take care of the real part, the entire plane. You know, when you have a real part, you are including the exponential e power sigma t or e power minus sigma t. And the very interesting observation I will tell you, by which you will understand what is the difference between these two. For example, I have e power at. E power at is a real exponential. Real, a is a real number. E power at is an exponentially increasing function. And I ask the question, can you find what is a Fourier transform for this? What is the Fourier transform of this? Sincerely, you will put the formula minus infinity to plus infinity. F of t is e power at multiplied by the transforming function e power minus j omega t dt. Then you will find e power a minus j omega into t divided by a minus j omega. But you have to substitute the limits minus infinity plus, and you stop there. You stop because you are getting infinity. One of them makes it infinity. If a is positive, when you put the positive value, it becomes infinite. What do you say then? Fourier transform does not exist for e power at. And you are right. But Laplace says, I am there to help you. So what do you do here? You are saying, what is the Laplace transform of same e power at? Come on, tell me. No, don't tell me the answer. Answer all of us. Integral minus infinity to plus infinity. Yes. I think here also it has got to be unilateral. Otherwise, it is a problem. It has got to be unilateral. Let me see. Having said it, let me see that. So, AT multiplied by e power minus st dt. St dt. So, it is equal to e power.
A minus.
Okay, a minus s or minus of s minus a into t divided by minus of s minus a. Again, one minute. S minus a, sigma. Positive. Unilateral exists, not bilateral. Bilateral does not exist. Unilateral thing, okay, 0 to infinity, it will exist. But ft does not exist. Even then, even if it is unilateral, it becomes infinity. Is it not? Because you have to put plus infinity. But Laplace transform, if you put this, what will happen? 0 to infinity? Tell me. When you put t is equal to infinity, it will be 0 provided. You have to tell me something. Oh, sorry. I think you are distracted. You are not focusing on my talk. Focusing on my... Okay. Can you tell me e power minus s of a into t? This is a constant, forget. If you put t is equal to infinity, will it be 0 or infinity? Come on. How? Because your s has got sigma plus j omega. J omega never gives a problem. Because its maximum value per mod of that one is 1. So this is equal to 0. So 0, that means t is equal to infinity, it will be 0. 1 divided by s minus a. Only if sigma minus a is positive. Can I say that? Because sigma is there in this real part is sigma. Sigma minus a. That should be positive. Then only t, when I put t is equal to plus infinity, it will be 0. Thanks to this minus sign before. So minus of something positive into t. So this will be 0 only if, or this is valid. You have to say sigma greater than 0. Sigma greater than 0 means if sigma must be greater than 0 means this is called the region of convergence. So we call it region of convergence. Where it converges, the region, any value after this sigma greater than a, sorry, I put it like this. This is the y-axis. This is a. So for sigma greater than a, that will be 0. Okay. So what is the summary of this? I don't know whether I answered your question or not. The summary is Laplace transform exists even though Fourier transform does not exist under some condition. That condition is ROC, region of convergence. We have to thank sigma. So we have to thank sigma. Okay? Okay, I think how many more minutes time is there? 10 minutes. I will spend 10 minutes for... Should I spend 10 minutes for your doubts clarification or go to DT? Discrete time signals.
Discrete time, sir.
Okay? I have not done any problems. Frankly, PPT I attempted, but I could not do anything. Okay, but I think it's okay. This kind of discussion was also different from other lectures. Right. So my question to you, before just, I will definitely close on time. How many signals are there in the orthogonal set for trigonometric Fourier series or complex exponential Fourier series? How many terms are there in Fourier series? Fourier series, how many terms are there totally? Infinite. Infinite cosine terms, infinite sine terms, only one term for DC, A0 by 2. That is a DC or constant value. That is okay, average value. Average or constant value. Okay. Now, that set of signals, a constant, A0 by 2, and all those signals A1 cos omega naught t and so on, B1 sin omega naught t and so on. This is called complete set of orthogonal signals required for Fourier series, trigonometric Fourier series. Is this set closed or complete? Is just closed or complete or both? We say a set of orthogonal signals is said to be closed when it is not closed. It goes on and on and on up to infinity, but it is complete. So that is the difference between, in many books also they write both are same. Closed set, complete set, they are not same. Okay, these are set of orthogonal signals which is closed but not complete. Which is complete but not closed, which is complete but not closed. But this is not the case with discrete signals. In discrete time domain, we have a closed complete set. But because you have only number of signals required to construct a periodic signal is limited. It's just n number. Capital N is the period, means n is the number of independent signals. Okay, why? Because if you take this e power j, you take the complex exponential in discrete time, we use k for the integer, e power j omega, we write 2 pi by n, 2 pi by t we write in continuous time, 2 pi by n we write in discrete time, into small n is the running time variable. Okay. I don't know whether you are with me or you get confused with this. You got confused? E power, in continuous time, what do you write? Complex exponential e power j n omega naught t, which is same as e power j n 2 pi by t into t. This is the continuous time complex exponential signals. Okay, you give different values to n, infinite values you get. They are all orthogonal, they don't know each other. Okay, right. Here I am putting j because it is complex. N, what is n here? Harmonic number. K here is the harmonic number, remember. We use n for, in place of the time variable, we write this. Okay, n 1, 2, 3, 4 like that, it goes on. It is a running discrete time variable. This is the continuous time variable. Nobody can stop its value. It takes values, all integer values here, any thinkable value here. Okay, so here you just take what is the periodicity of this. Periodicity of this is capital N. So if it is periodicity is capital N, then e power jk 2 pi by n multiplied by n plus capital N. What is the value of this? A signal f of t is periodic if f of t is equal to f of t plus or minus capital T for all values of t. That is the definition of periodicity. Okay, I move t seconds this side or that side, the same signal I must see. Then only it is periodic, same replica of this. So here I am adding n because n is the period. If I add n, what do I get here? E power j k 2 pi by n into small n multiplied by this into this multiplied by e power j k 2 pi. Ante kada?
And then we get the answer.
What is e power j k 2 pi? Cos 2 pi, cos k 2 pi or 2 pi k plus j into sin 2 pi k. So cos 2 pi k, because 2 pi k is 1, sin 2 pi k is 0. So you are getting 1, that means yes, n is the periodic. So, if I put n plus 1, you will get n plus 1 after n, next one is capital N plus 1. You will get the same signal. So, there are only n independent orthogonal signals that are enough. That is number one. The first difference between continuous time and discrete time exponentials or sinusoids is that the number of orthogonal signals required to construct a discrete time for periodic signal is finite in discrete, infinite in continuous time. So that is a great advantage because computer says no to anything that is infinity. We are making it finite. The one thing is delta of n, the impulse unit sample is well defined. It is 1 or 0. No discrepancy like delta of t. A lot of things we discussed. Delta of t is not computer friendly. Delta of n, yes, it is. So similarly, we have number of signals required is finite. Anything finite is comfortable. You ask me a million times, do the same thing, I will do. But don't say infinite times. Then it will stop working. Okay? That is I think we'll stop here. A lot of things I wanted to cover, but then I could not plan properly. PPT would have been better. I hope something I could share with you. I'm thankful very much to the management, to the faculty participants for giving me this. I totally stopped teaching 1.5 years back. Then my friend has asked me, why don't you talk to our participants? And I said, it is a good opportunity for me also to recall. I downloaded from my brain, frankly. I don't have any book with me, notes, everything I disposed of. And thank you. Thank you very much.